and share the screen. Can you see the screen, student?
Sir,
Yeah.
yes, sir.
Okay. Okay. You everyone give your role and batch your in the
Uh,
chat box. Everyone give your role and batch in the chat box. All. Okay. If I'm not wrong, we are studying the bipolar junction transistor. I know that some of the students have missed. For example, Misbah has come after a long time. So, it might be tough for him to cope up with the current class, because we have started a different topic, junction transistor, but let him try, and please see the previous video lecture, because I have given the video lecture, uh, and it will be also in the video lecture. So I think that it will no problem if you spend some time. So uh, before starting the class, in the last class we have studied the common base configuration. I said that my student, there are two mainly operations. That is, one is uh, the you know one is amplifier operation, another one is switching operation transistor. So we are studying amplifying operation, and in the amplifying operation there are three configurations. So today yesterday we saw one, that is the common base configuration. Today we will see the other two. One is common emitter, one is common collector. We all know that in a BJT transistor, suppose this is a transistor. Suppose this is a NPN transistor. Okay, so NPN transistor. So in NPN transistor, there are three terminal. One is base, the middle one is base, this one will be emitter, and finally it will be collector. Okay, so in the yesterday we discussed the common base configuration, where the base is common both in input and output. Today we will see the common emitter, the most popular configuration, and then we'll see the common collector configuration. Okay, then we'll start some one or two mathematics regarding the biasing of this transistor circuit. So that is our total plan of today. After this class, my students don't forget to attend the lab class, because after this class, yeah, on the last laboratory class I cannot conduct due to my sickness, but today I will show you the both those two, the rectifier and also the Zener dead operation. So please attend the laboratory class also. So we all know that in the transistor, this is the true thing, that emitter current is always the summation of collector current and the base current. Okay, emitter current is always equal to the summation of base current and collector current. So this equation will be always true for all configurations, for all type of transistor, either NPN or PNP. This equation is universally true, that emitter current is equals to collector current plus base current, where IB is a very small, the base current we all know is a very small, so that the emitter current and the collector current are quite like similar. The collector current is a little less than the emitter current, but as the base current is very small, so we can also take that IE is quite equivalent to IC, because of the IB is very small. So this can be taken. Okay, let's move forward. We saw the common base configuration in the yesterday class. Please, if you miss, see the class. So today we'll start from the common emitter. Okay, from the common emitter. So my student, common emitter, by the name you can definitely predict that the common emitter. So that means that emitter will be common. but emitter will be common. Common means both in the input side and the both in the input side and the output side. Okay, so that means that the emitter will be in the both input side and the output side. So here NPN transistor and PNP both configurations are given my student. So you can see from here on that that in the NPN transistor, the input will be across base and emitter. You can see that the input is across the base and emitter. This is the input side, base and emitter, and the output is collector and emitter. Okay, the input is base and emitter, and output is collector and emitter. So on that case, that's why you can say that that emitter is common both in the input side and the output side. It's similar in the PNP transistor also. The base and emitter is input, and the collector and emitter is output. So that's why it is known as common emitter configuration. So always remember that input emitter is both common in the input side and also output side. And we also know that to operate transistor for amplifier region, we need to make the transistor, we know that in the transistor there are two diodes available. So we need to make the emitter base junction forward, and we need to make the base collector junction reverse biased, isn't it? So you see that this is the base and emitter junction, this one. To make this forward bias, we need to connect this P with the positive and this N with the negative. So you can see that this P is connected with the positive and this N is connected with the negative terminal of the battery source. So that's why this PN junction, we can call it is forward biased. Similarly, this is the this junction is the collector base junction, and we need to make this junction reverse biased. So if we want to make reverse bias, so at that time we need to make uh, this junction reversed bias. So that's why we will connect N with the positive terminal and the P with the negative terminal. So you can see that this diode or this junction, the collector base junction, is reverse biased. So that's how we can make the transistor into the active region. We say that the first diode will be forward biased, and the second diode or the second junction, I'm talking about both junction and diode. Don't get confused. A junction is a diode. A PN junction is equals to a diode. Okay, that's why sometimes diode is known as PN junction. Okay, so don't get confused. So similarly, from here also you can see that the battery source, the IB is going here on, the IC is going here on. So we all know that the entering current equals to the exit current. So both the currents are entering inside the transistor. So the outgoing current is IE. So we all know that the IE is equals to IB, the base current, plus IC. Always this is always IC. This is always true for all configurations, for all type of transistor. Remember that the emitter current is always equal to the base current and the collector current. Okay, so from here on you see that this is the internal structure. This is the symbol, you can say that. So from here on we can say that the input is basically this voltage. The input voltage is VBE. The input voltage is VBE because the input is across the base and emitter, and the input current is IB. The input current is IB. Okay. And in the output circuit, we can say that the output voltage is VCE, collector and emitter, because the output is between collector and emitter, and the output current is IC. That means collector current. So that is the configurations of common emitter configuration. It is same also in the PNP junction. There is no change, just in the battery source connection will be different, because now it is PNP, not the NPN. So if we go to the next slide, you see that it is the test details is written here for your study purpose, and so you study that. Whatever I said right now, everything is written here. Everything is written here. So one important thing is that before going in the next slide, one important thing is that in the common emitter circuit, a new parameter is arrived, that is beta. In the common base configuration, we got alpha. Alpha equals to was the output current by input current. The output current was IC in the common base, and the input current was IE. Okay, so that was a useful equation. But in the common emitter circuit, we know that the input current is IB and the output current is IC. So what will be the current gain? The current gain is denoted as beta, and the denoted as beta is equals to the output by input. We all know that the gain is always the output by input. So in the output or gain efficiency, this type of parameter is always the ratio of output by input. Gain means what is the value we are getting in the output. Okay, please everyone give your role in the chat box. All give your role in the chat box. Okay, so the output current is IC and the input current is IB. Okay, my student, if you remember that I said that the IB is very small. IB is very small, so the value of beta is very big, because IC value is very big, IB is very small. So this value vary from 50 to 400. 50 to 400. So from here you can say that, or you can predict that the value of IB is so small, because the IB means the base current, and we all know that the base is very thin and very lightly doped. So the current across the base region is also very small. So this is the current gain, the DC current gain in the common emitter circuit. Okay, so basically it gains the output, the current. In the common emitter circuit, we get the high value of current in the output. So that's why it is also known as current amplifier, also known as, popularly known as current amplifier, because it amplifies the current. It amplifies the current. So those, now remember that these two equations. I will also show you in the next, but remember the two equations. These are the characteristics curve that in the input current and the output side. We all know that the input characteristics curve will be the input voltage and input current. The input voltage is IB and the input current is VBE, and the output current is IC and the output current is VCE. Okay, so from there we can say that, let me go to here. You see that here the input is across base and emitter, and this base emitter junction is forward bias. So the input curve will be the curve of the forward bias region of diode. Okay, the forward bias region of diode. And we see that in the collector emitter, this junction, the collector base junction, is reverse bias. So the output characteristics will be the reverse condition of diode, something like this. But this is in the reverse side, So if we replicate this, it will be something like this in the positive side. Okay, so output characteristics curve will be something like this. So if I go to the next slide, you can understand from here. You see that this is the forward bias region. This is the forward bias curve of diode, and this is the reverse bias curve of diode. But in the it is inverted. It is inverted. This is the output characteristics. So just this is not so important. Just make you see that the input current, the output current characteristics, just to predict. This is just I described, my student. I just described that the beta. What is the beta? Beta is the in the DC mode. It is the level of IC by IB. That is the output current and the input current. We know that in the input current is the base current, and the output current is the collector current. That's why if I divide, we get the gain. We get the gain, that is beta, and the value is 50 to 400. It depends on the doping purpose. If the doping is so much, at that time this beta is also bigger one. So remember this equation beta, and also one more equation we said that alpha. Alpha is the output current by input current. Output current was IC divided by IE. Okay, and the value of alpha, my student, the value of alpha is not so big. It is less than 1. It is less than 1, and its value is becomes probably its value is close to 0.95 to 0.98. Write on your paper 0.95 to 0.98. These are some critical information. The value of alpha is not big. It is close to 1, and the value is 0.95 to 0.98. But the value of beta is very big. It is 50 to 400. That's why it is called, because the beta is the current gain. That's why gain means we get much amount of current in the output with providing the less current. That's why this beta is known as the current gain, and the common emitter circuit or the common emitter transistor is known as current amplifier because it amplifies the current. Okay, so let me clear this. My students, please ask me any questions during the explanation if you face any difficulty. I try to go through as slowly as possible, but still, if I miss any information, if you face any difficulties about my explanation, please don't hesitate to question me. I'll be happy to answer to all of you. Now, if you got the two equations, now we got two parameter. One is alpha, another one is beta. Now let me find out the relations between these two, because it will be required when we go to the mathematics, different types of mathematics to solve these two parameters. I already discussed the alpha is the current gain, and the beta is also current gain, but the alpha value is less than 1. Okay, and the beta value is 50 to 200. And there are two equations. We know that here the beta is IC by IB, and the alpha is IC by IE. No, this comes from common base configuration. This comes from common emitter configuration. And we all know that, my students, we all know that IE equals to IC plus IB. These are the universal equation you need to know. You probably understand how this come from, but eventually I will suggest you that you memorize, because everyone will understand but if you don't remember at that particular time, it will be very tough. So you need to know that emitter current is equals to the collector current and the base current for all configurations, for all type of transistor. Okay, either NPN or PNP transistor, it is always same. So from here, in these equations, we can easily replace this value IE and IB in terms of IC. How? Because beta equals to IC by IB, so we can just multiply, cross multiply. Beta equals to, let me find out, beta equals to IC by IB. We just learned from here. So we can easily, my student, we can easily cross multiply and change the place. So at that time it will be IB equals to IC by beta. IC by beta. What we did, we just replaced this IV value from here with IC by beta. Similarly, we can replace from the alpha equation that IE equals to IC by alpha. Okay, IC by alpha. So from here on, we can remove IC from the both sides because these are equations. If we take common IC and in the right side and the IC available in the left side, so we can remove IC from the both sides. So finally we get 1 by alpha equals to 1 plus 1 by beta. Okay, so if we just cross multiply, finally we get alpha equals to beta divided by beta plus 1. From here also you can see that the beta divided by beta plus 1, that means the upper value is lower, because this is beta and the lower value is beta plus 1. So lower value or the denominator is a little bit bigger one. So suppose if the value of beta is 50, so that means this is 50, this is 51. So if I divide, use our calculator, the value may come 0.98 or 0.97. So which is eventually the value of alpha. I said that the value of alpha is closer to value of 1. Okay, so remember these equations just defined. So you can either so either or remember this the relations between alpha and beta. Okay, the alpha and beta, that alpha equals to always, this is very easy equations, alpha is equals to always the beta divided by beta plus 1. Okay, where alpha equals to IC by IE and the beta equals to IC by IB. And one more equation that is required, that is IE equals to IC plus IB. That means the emitter current equals to the collector current and the base current. So let me remove all the drawing and let me pass out the next. So eventually, my student, uh, these are the very interesting and equations. So it is also given here. So from here on, one thing is important, that we can see that the beta equals to as we just learned, that the beta equals to IC by IE, no sorry, is IC by IB. So from here on we can easily tell that IC equals to beta into IB, easily tell. Okay, so IC equals to beta into IB. So we can also find out the relations, here, that we are representing IC in terms of IB. We can also represent IE in terms of IB. How? Let's go to the main equation, that IE equals to IC plus IB. Here replace this value IC beta IB. Finally take the common IB. Finally we get that IE equals to beta plus 1 IB. Beta plus 1 IB. Remember, this is also a very important expression derived from the original expression, that IE is equals to beta plus 1 IB. Just the mathematical equations we find out from this. So these are the important equations. Please try to practice, try to understand. That's alpha equations, the beta equation, that alpha and beta relation, that beta divided by beta plus 1, and the main equation IE equals to IC plus IB. This equation is basically drawn from this beta equation. And finally we get the IE in terms of IB, where the beta is the current gain. Let me see that what is next. Okay, so this is it for the common emitter configuration. So now I will ask to my student, is there any questions, my student? Please don't hesitate. If I know, I will help. Is there any question, my student? Student, is there any questions from your side till now?
No, sir.
Abdul Rahman,
Sir,
any question? R7, who is R7?
No, sir.
yes, sir. No question, sir.
Are you
Unresolvable.
getting it? Amir, Amir,
Amir, बाहर निकला था.
Amir is here. Amir is here or not?
Amir, or Samir. Amir, how are you?
Okay, probably his net connection is a problem. So similarly, we this was the common emitter configuration. My student, that configuration is so popular because it increases the current. It increases the current. So it's so popular amplifier. Common emitter amplifier, so popular. So last but not the least, we will see the common collector configurations. The common collector. So from here on, we can also predict that now the collector will be common to both input side and the output side. So if you, as you can see here, that this is the collector now, this is the emitter, this is the base. So the base and collector is the input, and the emitter and collector is the output. So this is the exact same type of thing. If you get one or two, this will be the same. That the base and collector is now the input, and the emitter and collector is the output side. So we don't need to discuss this too much, because we already got it. Because now what will be the change? The change will be now the base and the collector will be in the input side, and the base and emitter will be the output side. The gain is there is a gain. There is a gain available in the common collector. Then the common collector gain is beta plus 1. The common collector gain is the beta plus 1. In the common emitter, the gain was alpha. In the common emitter, sorry, the common base was the gain was alpha. In the common
Was beta.
beta
Was common emitters.
That was common emitter. Now the common collector, the gain is represented as gamma, alpha, beta, gamma, and the gamma is basically beta plus 1. Okay, the gamma is basically beta plus 1, but gamma is not basically used. So that's why that word is not used, because of it might confuse you with the three specific parameter. So that's why the gamma is nothing, just the beta plus 1. The beta plus 1, that is the current gain in the output in the common collector circuit. So common collector circuit is not so important, something like that in terms of operation. It is used in impedance matching. So finally, there is a table. There is a comparison table. From here, you can compare easily that what is the input impedance. Impedance means resistance. In the input resistance, the common base is low, the common emitter is medium, and in the common collector, that is high. And the output impedance, the common base is very high, the common emitter is high, and finally the common output impedance is low, and the common collector is low. Interesting thing is that from here on, that phase angle 180 degree. In the common emitter, I forgot to discuss this one, that what is 180 degree phase shift. Let me go to the common emitter one more time. Okay. Yes, this one. This one is the common emitter. So if you see that, my students, this is the input side, base and emitter. Okay, this is the input side. So we can easily take the input side. This is plus, this is minus. So the voltage will be plus minus. But you see that in the output side, the current is flowing in the opposite direction. The current is flowing in the opposite direction. So if there is a, suppose if there is a resistance here, if there is a resistance here, if the current flows across this resistance, this will be positive terminal, this will be negative terminal, because we all know that when the current starts to flow across the load, the entering point becomes positive and the outgoing point becomes negative. Okay, so at that time, if I want to calculate the the output voltage, because we all know the output is across the collector to an emitter, so this will be positive, this will be negative. So what we'll get, we'll get the negative voltage. Okay, because of the current configuration. So that's why it is 180 phase shift, means that you are giving in the input as a positive but getting negative. Okay, that's why it is 180 phase shift. Suppose if your AC voltage, suppose suppose this is your AC voltage, and the output you will get something like that. That is 180 phase shift. So basically, um, my student, in the common emitter circuit, we get the opposite voltage. That means the opposite sign of voltage in the output. That's why it is known as the 180 phase shift in the output. So finally, these are the power, how much voltage they get. We say from here we can see that the both in the common emitter, and the voltage gain and the current gain are both are medium. So that's why this is the most popular, because from here we get the maximum power. Okay, so because the both the value are medium, that means medium means not less not high. So from here on we can easily get we can easily get the maximum amount of power. That's why it is the most popular. The common emitter circuit is the most popular circuit. Before going to the mathematics, these are the important equations that I'm discussing thoroughly. Again, this is the emitter current equals to collector current plus base current. You need to know this is the collector current equation, because we all know that collector currents are basically for two reasons. One is for majority carrier, one is for minority carriers. Okay, in the base emitter, as it is a forward bias, so that's why due to silicon we all know that the forward bias voltage, that is the 0.7 voltage. So always remember that the base and emitter voltage, that is always 0.7 volt, the 0.7 volt, my student. So finally, uh, you know the alpha equals to IC by IE, the beta equals to IC by IB, and from here we can also say that the IC equals to beta into IB, and we also derive that the IE equals to beta plus 1 IB, beta plus 1 IB, and also the relations between alpha equal and beta equals to alpha equals to beta divided by beta plus 1, beta plus 1. So these are the important equations you must know after whatever we study, because when we go to the mathematical problem, these equations will be required more and more. So try to keep on your mind this alpha equations, the beta equations, the relations between the IC, IB, and IE. If you have two equations, so you can easily make the relations between IC, IB, IE. And if you have alpha and beta equations, if you have alpha you can get the beta, if you have beta you can get the alpha. So easily possible. And this is the mother equations, the emitter current equals to IC plus IB. So these equations please try to at least practice in home. So now we start with the first type of example, that how to bias. Bias means making the transistor in the active region. You know, we all know that the transistor, to make transistor in the active region, the first junction, the base emitter junction, should be forward biased, and the collector base junction should be reverse biased. So this is the fixed bias configuration. Like we see that here, but till now we didn't discuss about the resistance. But we all know that in input we use a resistance so that the current keeps in the limited region. Okay, when you do not give a resistance, the huge amount of current will flow. So that's why there is a resistance in every side. In the input side and the output side is always given. So here you can see that the base emitter collector, it is connected in between. Okay, so this is the RB is the base resistor, the RC is the collector resistor. Okay, and from collector we get output, and from the base we give input. So from here easily you can say that this is the base to emitter, that means this is input, and this is collector to emitter, that is output. So we can easily say that this is kind of common emitter configuration, the kind of common emitter configuration. Okay, so you see that this is the AC input signal, this is the AC output signal. So this is not required right now, because right now we are dealing with the AC, not AC, we are dealing with the DC. So this is the biasing. So in the DC, when we apply DC, this capacitor will be open circuit. Why? Because we all know that the DC, the frequency is 0, F equals to 0.
Yes, yes, sir.
Isn't it?
Yes.
Frequency is equals to 0. So when you go for the impedance, X equals to 1 by, my student, twice pi FC, isn't it?
2 bytes, yes, sir.
Yes, 2 pi FC. So
Yes,
as the F
X.
is 0, so the value will be 1 by 0. That is,
0.
no, 1 by 0 is infinity.
Yes, yes, infinite, sir.
1 by 0 is infinity. So that means that at DC, the capacitor will be open circuit. Yeah, that means the no current flow will be in this terminal. Okay, and we also discussed this type of notation. If you remember in the diode circuit, that this type of notation, this is small circle, and in the between this is plus V, plus 5. So that means this is the plus 5 voltage. Here VCC, it is plus VCC voltage. And you see that these two terminal, both in the base and collector, both are taking common here. So that means we can also divide this VCC into two parts, because this, from this point it is also VCC, and at this point it is also VCC. So those are both are connected together and just connected with the VCC. We can either take this as a common, or we can divide into these two terminals. Okay, so let's go to the next slide, which will have a much more detail. Here you can see that, my student, as we are discussing with the AC, so this DC, sorry, we are discussing with the DC, so that's why the capacitor are open circuit. The capacitor are open circuited, and this VCC we can divide into two sections, because you know we all know that these are connected together, and we can also divide into two sides VCC. Okay, so from here on we will let's calculate what is the output current, let's calculate what is the output voltage, and let's calculate what is the input current IB. And in the what is the input voltage VBE, can anyone tell what is the value of the VBE?
0%, sir.
0.7. Yes, absolutely correct, because this is the base and emitter, and we all know that the base emitter, that is forward biased, and in the forward bias we all know that the voltage is 0.7 volt for silicon. Always remember this. Always remember this. The VE is equals to 0.7. It's 2.7. Okay. Let me go to. So first of all, you see that if I go to the previous slide. So first of all, we calculate the input side. This is the input side, you know, the base and emitter, and we will calculate the output side, you know, separately. Both these things are separately. Okay, Amir is here, my student Amir.
Amir,
Amir, is there any problem to him? He always responds. I don't know. Okay, no problem. So we will calculate the input side separately and the output side separately. Okay, so let me go to that, the input side first of all. My students, if you notice that here, what is the change? Here the change is this VCC is connected in the input side. We can write this VCC as it is a positive, so the battery positive terminal will be nearest to that. So we can write this something like that. Here, this is connected with the ground. Okay, so the value will be, this battery cells will be VCC. This will be positive terminal and this will be negative terminal. So this is exactly the same thing done in the next slide. You see that? It's exactly the same thing. Sorry, it is probably cut out. This is VCC. This is VCC. This is that. This point VCC is just distributed. We all know this is notation. If you forget, it is probably shown in the third class, in our third class of video lecture, or you can say you can also check the topic, the diode circuits, the PDF that is given here. This type of, this is called source notation. This type of notation we can divide. So this is here. Now what can we do, my student? What can we do? We can easily, because these two terminals are shorted, so there is a loop here available. There is a loop available here. So we will apply a KVL here. If we apply KVL, my student, if we apply a KVL, what we get? What we get? We get, first of all, this is the plus. We are taking the second sign. So the VCC plus VCC. Then we're taking the second sign, because in this circuit, the current is IB, the input current IB. So it will be RB into IB. You see that, minus RB into IB, because we are taking the second sign. And finally, this plus minus VBE, plus minus VBE will take the second sign. So basically it will be minus VBE. Okay, equals to 0. We apply the KVL in the input side. We apply the KVL in the input side. So if we take, if you replace take this in the other side, and finally we put the RB in the other side, we get that the input current IB equals to VCC minus VBE divided by RB. So suppose in the example, the RB value will be given, the VCC will be given, and we all know that what is the value of VBE. The VBE is the 0.7, so we can easily find out the IB, isn't it, my student? We can easily find out the IB. Suppose if the beta value is given, at that time we can also find out the value of IC. Why? How? Because we can easily find out the value of IC, because we all know that if we multiply with the beta into IB, we get the value of IC. So that's why those equations are very important, my students. Very important. Okay. So this is in the input side. Let me go to the output side. You see that this is the output side. The same thing. Just give me one more time. Okay, wait. So You see that here in the output side, you know, these VCCs, you know, just because at that point that was VCC, we just distributed this VCC into this side. Okay, so now we can also make a loop. Okay, now we can also make a loop. How? Suppose we make a loop here in this conditions. So similarly, at that time it will be suppose the first of all the plus VCE. If we are taking the second sign, my students, remember that the current is flowing from this direction. So the RC plus will be this. The RC plus will be this. So you know the first sign will be the plus VCE. So the next will be the IC RC because the current is IC, and finally we're taking the second sign as it is. It will be minus VCE. It might be confusing to you, but my student, we are taking the loops in this direction, but the current is flowing in this direction. Okay, so first of all, you know that we need to place the sign of current. At that time, so after that, you know, you can easily take the either first sign or the second sign. So for the VCE, we take the first second sign. For this RC, we take the second sign, and finally we take the second sign of the VCE. So we take the you know, the KVL, and finally we need to find out the output voltage. The output voltage is basically, my student, the output voltage is basically the VCE,
VCE, sir.
the collector and emitter current. So we take VCE one side, and the other side VCC minus IC RC. VCC minus RC IC RC. Okay. So here VCC will be given. IC current we can easily find out from that beta IB, and RC is also given, so we can easily find out the output current. Output voltage VCE. Okay. My students, wait for 1 minute. Just I got a call from department. Just Sorry, my student, what I was discussing that the VCE, the output voltage, okay, the VCE. You can also say that, my student, the VC is basically the potential difference between the collector and the emitter, okay, the potential difference between the collector and emitter. So this is the point of VC, the collector voltage, this is the point of VE. So from here, my student, you can see that the emitter voltage is 0 because the emitter is connected with the ground, so the voltage of it will be 0. So from here the VCE will be equals to VC, which is also it is also true. The VCE equals to VC. So in the next, it is also written here. You see that as the VE is, VE is 0. So from here, the VCE equals to VC. It is also, we can write. And finally, as we all know that the VBE, that is in the potential difference between the VB and the potential difference between the VE. So this is the difference. We all know that the VE is 0. So we can easily place the value 0 here, and we can the VBE equals to VB. So we can also, this can also be done if there is if the emitter is directly connected with the ground. Okay, so this might help you in the example. So this is just was the demonstration. Let's go an example and find out that what is given here. So this is an example. First of all, let me show you that first of all, it is given here. The VCC is given at 12 volt, and the VCC is 12 volt. The beta is 50. That means the amplification, current amplification is 50. That is given here. And the RB is 240 kilo ohm. The RC is 2.2 kilo ohm. And input is IB current, and the output current is IC current. So it's given here. So what is told? We are told that to find out the current IB and IC. That means input current, output current you find. Then you find out the output voltage VCE, the output voltage VCE. Then you find out the point potential, exact point potential VB and VC, and finally VBC. Okay, so we just showed you the how to find out the point VE. We just showed. Okay, let me go to the example and find find that how we need to find out. From here, we already discussed that if we divide this 12 volt in the both sides, and if we KVL, apply the KVL in the positive in the input side, we get this equation IB equals to VC. We just showed IB equals to VCC minus VB. If you don't understand how to get you just see the previous slide that we just divide. This is 12. This will be 12. This is connected into this. Okay, and apply the KVL here. So here the VCC is 12 volt, the VB is 0.7 volt, and the RB is given 240 kilo ohm. That is 47.08 microampere. This is the very tiny current in the base. Now if the beta is given 50, so we can easily multiply with this beta and get the IC current. You see that IC equals to beta into IB plus IB. If you multiply this, we get the current IC also. Okay, so IC also we get this. First A is done, and the next, that was find out the VCE. The VCE, my student, if you see properly, this point is 12 volt. This point is 12 volt. This 12 volt is divided into this and these two region. Okay, so if we somehow find out this voltage and subtract from 12, the rest of the voltage equals to the VC, isn't it? Because we all know that the KVL equals to the summation of drop voltage equals to total voltage, input voltage. Yeah, the 12 volt is given here. So this 12 volt will be applied this resistance and this VCE. So that's why from this resistance voltage, how we can find out the Ohm's law, IC into RC. The current is flowing here is IC. So you know the total 12 minus IC into RC, we just find out the IC value. So this 6.83 is the voltage of VCE. The next two is that find out next two is the find out the VB and the VC. That is this potential and this potential. So this potential VB, we all know that the VBE equals to VB minus VE. We just find out VB minus VE. Here we can see that, sir, the VE is 0. So if you replace the 0, that means the VBE is equals to VB. We all know that the VBE value is 0.7. So that's why you see that the VB equals to 0.7 volt. In the similar manner, the VCE, the point VE, the voltage at point A, emitter is 0. So that's why the VC equals to the VCE 6.83. Just we discussed earlier. Finally, we need to find out the VBC. VBC means VB minus VC. This point and this point voltage difference. So we write VB minus VC. We get two voltage 0.7 and point. Finally, we get the minus 6.13. Why this negative sign? Because the negative sign reveals that the junction is reversed bias. The junction is reversed bias and it should be linear amplification. The linear amplification, that means the amplification will be linear. The amount of voltage increase, the amount of current we get. So this is a reverse bias. That's why the current, the voltage value is minus. So in this way, we will solve the transistor problems. It's very easy. You see that just the equations we learned, some of the basic equations. If I go to back side, this is. If we go to back side, before discussing this, these equations are very, very, very important, my student. These equations, you see that we used this equation directly, we use this equation directly, we might use this equation, we use this equation directly. So we already used these three equations from one example. So, and this is the mother equation, the I equals to IC plus IB. Okay, so that's why in this way we will solve we will solve rest of the day. So that's it for today in the theoretical class. Now I will tell all my students and I will unmute all my students. Is there any question from your side? Let me unmute. My students, is there any question from your side?
No, sir.
No, sir.
Mashallah.
No, sir.
Is it
It is
looking?
understandable lesson, sir.
Is it hard to you, my student? Is it hard to you?
No, sir. No, sir.
I'm trying my best to make you understand, but still might and some.
Sir, it is under.
Una cambia di quella tutta. Don.
Okay. Okay, let me please everyone try to give your role in the chat box. All. Let me mute one and try to give your role in the chat box. Everyone. I'm writing the row batch 29, roll 21, batch 30, roll 3, then the batch 30, roll 2, batch 30, roll 2, batch 30, roll 8, the batch 30, roll 14, batch 29, roll 16, batch 30, roll 13, batch 29, roll 8, Batch 29, roll 3. Batch 29, roll 1. Batch 29, roll 7. Please give your roll in the chat box. I'm collecting the information. Batch 29, roll 4. Batch 30, roll 4. So that's it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Is there anyone else, my student? Is there anyone else?
Maybe no, sir.
I think no one, sir. No one
Okay.
else.
Okay. Now I am giving you 15 minutes break. We will start our laboratory class at 11:45. Clear? Okay.
Okay, sir.